Hello, gentle dreamer. Welcome back to another quiet journey through the cosmos. Some nights you look up and see a point of light, just one, steady, small, and you think, that's a star. But what if I told you that tiny spark barely visible to your naked eye could swallow our entire solar system? What if that whisper of light is actually a titan, breathing fire across distances so vast that the number itself becomes meaningless? Tonight, we're not just looking at stars. We're drifting toward the giants, the largest stars ever discovered. Stars so immense that if you place them where our sun sits, their edges would reach past Jupiter, past Saturn, into the cold, dark beyond. And yet, from Earth, they look like nothing more than a gentle flicker. Before we begin this quiet voyage, if you find comfort in these slow stories of the universe, you might like to stay a while. You can gently tap the like button, subscribe if you would like more nights like this, and ring the little bell, not for noise, but so the next quiet journey can find you again. Thank you for being here. Now, let's drift. The universe has a way of hiding its largest secrets in plain sight. Right now above you, scattered across the darkness, there are stars so colossal that our sun, the ball of fire that lights every dawn you've ever known, would be no larger than a pixel on your screen in comparison. And the strangest part, you've probably seen them. You've stared right at them and had no idea. That's the gift and the trick of distance. Space doesn't just separate us from the stars, it disguises them. It shrinks giants into glimmers. It turns monsters into myths. And for most of human history, we had no idea we were being so gently deceived. Think about it. When you stand beneath a night sky, you see thousands of stars, maybe more if the sky is clear and the moon is soft. Some are bright, some are dim, some flicker, some hold steady. But brightness, it turns out, has almost nothing to do with size. In fact, some of the brightest stars you see, stars like Sirius blazing blue-white in the winter sky, are not even close to being the largest. Sirius is brilliant, yes. It's about twice the size of our sun. But twice the size of the sun is still small, modest, humble even in the scale of what's truly out there. Scientists suggest that the confusion comes from one simple fact. What we see is not what is. We see apparent brightness, the light that reaches us after traveling for years, decades, sometimes centuries through the void. But the true size of a star, the actual diameter of that burning sphere, requires something more than eyesight. It requires mathematics, spectroscopy, patience. It requires us to measure not just the light that arrives, but the light that left, and to understand the difference. Let's take Betelgeuse, for example. You've probably heard of it. It's the red giant marking the shoulder of Orion, that constellation so many of us learned to find as children. Betelgeuse is bright. It's one of the 10 brightest stars in our entire sky. And yet, it sits over 600 light-years away. If Betelgeuse were as close to us as Sirius, just 8.6 light-years away, it wouldn't be a star anymore. It would be a sun, a second sun. It would cast shadows at night. It would change the color of our sky. Because Betelgeuse is not twice the size of the sun. It's not 10 times or 50 times. Research shows that Betelgeuse is roughly 700 times larger in radius than the sun. If you placed it at the center of our solar system, its outer layers would reach past the orbit of Mars. Earth would be inside it. Venus would be inside it. We would be consumed not by fire in the way we imagine fire, but by a kind of light so diffuse, so gentle in its vastness, that it hardly seems violent at all. And yet from here, Betelgeuse is just a dot, a red dot, pulsing softly, quiet. This is the illusion we live with. Distance is the kindest liar in the universe. It lets us sleep beneath a sky full of giants without ever feeling small. But here's where it gets strange, where the universe starts to lean into paradox. The largest stars we know of are not always the brightest ones we see. In fact, many of the true titans, the stars that make Betelgeuse look modest, are so far away, or so cool in temperature, or so obscured by dust, that they barely register to our eyes at all. Some of them weren't even discovered until the late 20th century, when our instruments finally became sensitive enough to see through the veils. Take VY Canis Majoris. Located about 3,800 light-years away in the constellation Canis Major, this star is so large that if you tried to drive around it at highway speed, it would take you over 20,000 years to complete one lap. And yet, you can't see it without a telescope. Not because it's faint in any absolute sense, it's one of the most luminous stars known, but because all that light has to travel so far through so much space that by the time it reaches us, it's dimmed to invisibility. Some believe this is the universe's way of protecting us. Imagine if we could see these stars as they truly are. Imagine if every giant in the galaxy appeared in proportion to its actual size, glowing with the full weight of its power. The night sky wouldn't be a place of rest. It would be overwhelming, blinding, a canvas too bright to bear. Instead, we get softness, we get mystery, we get a sky that invites us to wonder without demanding that we understand. And that's the strange mercy of it all, isn't it? The largest things in existence are hidden by their own distance. The most powerful lights are softened by the time it takes for them to reach us. Even the universe in all its violence and scale knows how to whisper. So, tonight as we begin this journey into the realm of giants, I want you to hold that thought. The stars you see are not what they seem. The tiny sparks above you might be forges large enough to hold planets, winds fast enough to strip atmospheres, fires old enough to have been burning since before humans learned to speak. You are looking at history. You are looking at physics made visible. You are looking at time itself, frozen in the act of traveling toward you. And the beautiful part, you don't need to understand it all. You don't need to calculate the distances or memorize the names. You just need to know that the universe is bigger than it looks. That light can be both honest and deceptive, that even stars in their immensity can learn to hide. We'll drift quietly through this tonight. We'll meet the red giants and the blue hypergiants. We'll walk through the mathematics of measurement and the poetry of collapse. We'll learn how scientists weigh something they can't touch, how they measure something they can't circle, how they name something that existed long before names were invented. But right now in this moment, all you need to do is breathe. Let the wonder settle in softly. Let the questions arrive without urgency. Because the stars those distant giants have been waiting for billions of years. They're not going anywhere, and neither are we. What seems small may be holding entire worlds inside its glow. What seems distant may be closer than we think if we measure closeness not in miles, but in meaning. The universe is full of things pretending to be smaller than they are. And maybe so are we. So, let's begin. Let's step gently into the dark and see what the giants have been hiding. Let's learn why size in space is the most beautiful lie ever told. The human eye is a beautiful instrument. It can detect a single photon in absolute darkness. It can distinguish millions of colors. It can track movement, recognize faces, find patterns in chaos. But when it comes to stars, when it comes to measuring the true giants of the cosmos, the eye becomes something else entirely. It becomes a storyteller, and like all storytellers, it bends the truth to fit the narrative we can bear to hear. For thousands of years, we looked up and believed what we saw. The brightest stars were the most important. The dimmest were the least. It made sense. It felt true. The ancient Greeks built an entire system around this idea, categorizing stars into 6 magnitudes based purely on how bright they appeared to the naked eye. First magnitude stars were the brilliant ones, Sirius, Vega, Arcturus. 6th magnitude stars were barely visible whispers on the edge of perception. It was elegant, simple, completely wrong. Because brightness, it turns out, has almost nothing to do with size. And size has almost nothing to do with importance. What we see when we look at the night sky is not a map of reality. It's a map of consequences. The consequence of distance, of temperature, of chemistry, of time. Every star is telling us a story, but the story we hear is filtered through hundreds, sometimes thousands of light years of empty space. By the time the light reaches us, the plot has changed. Let me show you what I mean. Think of Sirius again, that brilliant blue-white diamond in the winter sky. It's the brightest star we can see from Earth, excluding the sun. If you've ever looked south on a cold January night, you've seen it. Impossible to miss. Ancient sailors used it for navigation. Poets wrote about it. Entire calendars were built around its rising. It feels powerful, doesn't it? It feels important. And it is. But not because it's large. Sirius is roughly 1.7 times the diameter of the sun. That's it. It's not a giant. It's barely even a grown-up. Sirius is bright because it's close only 8.6 light-years away, and because it burns hot over 9,000 degrees Kelvin at the surface. It's proximity and temperature doing the work, not size. Now compare that to a star like Antares. Antares sits in the heart of Scorpius, glowing red and steady. To the naked eye, it's bright, yes, but not nearly as bright as Sirius. In the magnitude system, Antares is ranked around 1.2, while Sirius blazes at minus 1.46. The difference seems small, but here's the twist. Antares is over 550 light-years away. It's 64 times farther from us than Sirius. And yet, despite that distance, despite the fact that its light has to travel across more than half a millennium of space to reach us, it still appears nearly as bright. Why? Because Antares is enormous. Scientists suggest that if you placed Antares where our sun is, it would extend past the orbit of Mars. It's roughly 700 times larger in radius than the sun, over 10,000 times more luminous. If Antares were as close as Sirius, it wouldn't just be the brightest star in the sky. It would be visible during the day. It would rival the moon. This is the illusion. This is the trick that space plays on us. Distance compresses power. It makes monsters look like fireflies. It equalizes the unequal. And for most of history, we had no way of knowing. We thought brightness was truth. We thought what we saw was what existed. The shift came slowly starting in the 17th century. Astronomers began to realize that stars were not all the same distance away. Parallax measurements watching how a star's position shifts as Earth orbits the sun allowed them to calculate distances, at least to nearby stars. And once you know distance, you can work backward. You can ask, if this star is 50 light-years away and appears this bright, how bright must it actually be? That's when the term absolute magnitude was born. Not how bright a star looks from Earth, but how bright it would appear if placed at a standard distance of 32.6 light-years. It's a way of removing the disguise, a way of seeing the star as it truly is. When you do that math, the hierarchy collapses. Sirius, so brilliant in our sky, has an absolute magnitude of about 1.4. Respectable, but not remarkable. Antares, meanwhile, has an absolute magnitude of around minus 5.3. If you could line them up at the same distance, Antares would outshine Sirius by more than 600 times. The giant was hiding behind the curtain of space, pretending to be something smaller, quieter, less significant. But it was there all along, waiting to be calculated, waiting to be understood. Here's where it gets even stranger. Temperature matters as much as size, sometimes more. A star's color tells you how hot it is. Blue stars burn hotter than white stars. White stars burn hotter than yellow stars. Yellow stars burn hotter than red stars. And the hotter a star burns, the more energy it radiates per square meter of surface. So, a small hot star can outshine a large cool star, even if the large star has more total surface area. It's like comparing a blowtorch to a campfire. The blowtorch is tiny, but it's intense. The campfire is big, but it's gentle. From a distance, the blowtorch might look brighter, even though the campfire is physically larger. This is the mistake so many people make when they first start learning about stars. They assume brightness equals size. They assume the stars that dominate the night sky are the titans. But brightness is just one variable in a long, complex equation. Size is another. Distance is another. Temperature, luminosity, chemical composition, age, they all matter. they all distort the picture. And the universe in its quiet indifference doesn't bother to explain itself. Research shows that even professional astronomers struggled with this for decades. In the early 1900s, when spectroscopy became refined enough to measure the light signatures of distant stars, scientists started noticing something odd. Some stars emitted spectra that suggested they were cool red low energy, but they were also incredibly bright. That didn't make sense. A cool star should be dim unless it was massive, unless its size compensated for its low temperature. That's when the term supergiant was coined. Not just a giant, a supergiant. A star so large that even burning cool, it could flood the cosmos with light. And suddenly, the night sky transformed. What looked like a scattering of random lights became a taxonomy, a family tree of stellar evolution. There were main sequence stars like our sun burning steady and modest. There were white dwarfs tiny and dense and fading. There were red giants swollen and old, and there were the supergiants, both red and blue, titanic in scale, catastrophic in power, brief in lifespan. The universe wasn't simple. It was layered, deceptive, full of things pretending to be what they weren't. Let's talk about one more example because I think it captures the illusion perfectly. There's a star called Mu Cephei, also known as Herschel's garnet star. William Herschel, the astronomer who discovered Uranus, called it a very fine, deep garnet color when he observed it in 1783. It's one of the reddest stars visible to the naked eye, and it sits about 6,000 light-years away in the constellation Cepheus. To most people, it's invisible. You need to know where to look, and even then it's just a faint ruddy smudge. Nothing impressive, nothing worth writing home about. But Mu Cephei is a red supergiant with a radius over 1/200 times that of the Sun. If you placed it at the center of our solar system, it would swallow Mercury, Venus, Earth, Mars, and potentially Jupiter. Its surface would be somewhere between the orbits of Jupiter and Saturn. It's one of the largest stars known, and yet from Earth it's nearly invisible. Why? Because it's so far away that even its immense luminosity, about 350,000 times that of the Sun, gets spread thin by distance. Because it's so cool around 3,700 Kelvin that most of its energy radiates in infrared wavelengths we can't see with our eyes. Because the universe is so vast that even something as large as Mu Cephei can get lost in the noise. This is the lesson, the quiet truth beneath all the math and the measurements. The universe doesn't care what we see. It doesn't adjust itself for our convenience. It simply is. And what we perceive, the brightness, the arrangement, the shapes we turn into constellations, is just a shadow, a projection of something far stranger and far larger than we can intuitively grasp. Distance is a filter. It softens the edges. It equalizes the unequal. It makes the vast seem small and the near seem significant. And for most of human history, that filter was invisible to us. We thought we were seeing the stars as they were. We didn't realize we were seeing them as distance allowed us to see them. But now we know. Now we have the tools to pierce the veil. We can measure the spectrum of a star's light and deduce its temperature. We can track its parallax and calculate its distance. We can analyze its luminosity and estimate its size. We've learned to see past the illusion, to decode the lies that light tells on its long journey toward us. And what we've found is humbling. The stars that dominate our sky are not the largest. They're just the closest or the hottest or the luckiest in terms of line of sight. The true giants are out there hidden in the deep, dark, burning, slow, and red, and impossibly vast, waiting for us to notice, waiting for us to do the math. It makes you wonder what else we're missing, doesn't it? What other giants are lurking just beyond the limits of perception, disguised by distance or temperature, or some other variable we haven't learned to measure yet? The universe is full of illusions. Full of things that look small but are enormous, things that look dim but are blazing, things that seem close but are impossibly far. And the more we learn, the more we realize how much we still don't see. The eye is a beautiful instrument, but it was never meant to measure infinity. It was meant to navigate Earth, to recognize kin, to find food and shelter and safety. The stars were always too big for it, too strange, too far. And maybe that's okay. Maybe the illusion is part of the gift. Maybe not knowing how large the giants truly are is what lets us sleep peacefully beneath them. But for those of us who want to know, who need to understand, the tools are there. The equations are waiting. The universe, for all its deception, is ultimately honest. It hides its giants, yes, but it leaves the clues. And if we're patient, if we're careful, we can follow them. We can peel back the layers of light and distance. We can see the stars not as they appear, but as they are. And when we do, the night sky transforms. It stops being a decoration. It becomes a battlefield of physics, a graveyard of time, a nursery of atoms. It becomes real. And the giants, those hidden titans burning slow and vast in the dark, step out of their disguises and show themselves for what they've always been. Monsters made of light, forges larger than comprehension. Stars so immense that calling them stars feels inadequate, like calling an ocean a puddle. But we're not there yet. We've only just started to pull back the veil. There's more to uncover, more stories hiding in the dark. And the question now becomes, how did we even find them? How do you discover something that's invisible? How do you measure something you can't touch, can't circle, can't even see clearly? That's where the real journey begins. Discovery is rarely loud. It doesn't announce itself with trumpets or flashing lights. Most of the time, discovery is a whisper in data, a number that doesn't fit, a pattern that shouldn't exist. And sometimes discovery is simply someone looking at the same thing everyone else has seen, but asking a different question. The largest stars in the universe were found exactly that way. Not by accident, not by luck, but by patience, by instruments sensitive enough to detect what the eye could not, and by scientists willing to trust mathematics over intuition. Because here's the truth, the invisible titans were never really invisible. They were always there burning in the dark. We just didn't know how to see them yet. Let's go back to the beginning, the early 1800s. Astronomy was still young, still finding its language. Telescopes had been around for 2 centuries, but they were crude, limited to visible light, and plagued by distortion. Most astronomers were focused on mapping the positions of stars, tracking planets, calculating orbits. The idea that you could measure a star's size, its temperature, its composition, that felt like fantasy. How do you weigh something you can't touch? How do you measure something millions of miles wide from billions of miles away? It seemed impossible. But then, in 1814, a German optician named Josef von Fraunhofer did something strange. He took sunlight, passed it through a prism, and instead of just marveling at the rainbow, he looked closer, and what he saw changed everything. The spectrum wasn't smooth, it was interrupted. There were dark lines cutting through the colors, thin black gaps, where certain wavelengths of light were missing. He didn't understand what he was seeing at first. No one did. But he cataloged them anyway. Hundreds of lines, precise, repeatable, mysterious. It took decades to figure out what those lines meant. Scientists like Gustav Kirchhoff and Robert Bunsen eventually realized that each chemical element absorbs and emits light at specific wavelengths. When you heat sodium, it glows yellow. When you heat hydrogen, it glows red with a touch of blue. And when light passes through a gas containing those elements, it leaves a fingerprint, a unique pattern of dark lines in the spectrum. Fraunhofer's lines weren't flaws in the sunlight. They were messages. They were the sun telling us what it was made of. This was the birth of spectroscopy, and it was revolutionary, because suddenly you didn't need to travel to a star to understand it. You just needed to capture its light. You could point a telescope at a distant sun, split its light into a spectrum, read the lines and know, truly know, what elements were burning inside it. Iron, carbon, helium, calcium. The universe was no longer opaque. It was readable. But spectroscopy gave us more than chemistry. It gave us temperature. It gave us velocity. And eventually, it gave us size. Here's how. When you study the spectrum of a star, you notice something about the lines. In hotter stars, the lines are sharp and well-defined. In cooler stars, the lines are broader, fuzzier, sometimes blended together. That's because temperature affects how atoms behave. Hot atoms move fast, collide often, and produce clean, distinct spectral signatures. Cool atoms move slowly, interact more gently, and their light gets smudged by molecular bonds and lower energy states. Scientists suggest that by analyzing these subtle differences, you can determine the surface temperature of a star to within a few hundred degrees, even if that star is thousands of light years away. And once you know temperature, you can start estimating size. Because a star's luminosity, the total amount of energy it radiates, depends on two things: how hot it is and how much surface area it has. It's like comparing a light bulb to a bonfire. A single 100-watt bulb is hot and bright, but it's small. A bonfire is cooler per square inch, but it has so much surface area that it outshines the bulb. Stars work the same way. If you measure a star's luminosity and its temperature, you can solve for radius. The math isn't simple, but it's reliable. And that's how, in the late 19th and early 20th centuries, astronomers began to realize that some stars were far, far larger than anyone had imagined. One of the first supergiant stars to be recognized was Betelgeuse, and the story of its discovery is worth sitting with for a moment. Betelgeuse had been known since ancient times. Ptolemy mentioned it. Arab astronomers cataloged it. But no one thought of it as unusual. It was just a bright red star in Orion. Then in 1920, two astronomers named Albert Michelson and Francis Pease did something no one had done before. They used a technique called interferometry to directly measure the angular diameter of Betelgeuse. Essentially, they combined the light from two separate telescopes, creating an interference pattern that revealed the star's apparent size in the sky. And what they found shocked the scientific community. Betelgeuse wasn't a point of light. It had a measurable disk. It was enormous, so large that if you placed it where the sun is, it would extend past the orbit of Mars. Think about that. For the first time in human history, we had proof that stars could be giants. Not metaphorically, not poetically. Actually, physically, monumentally huge. The universe had been hiding this from us for millennia, and now with the right tools, we could finally see it. But Betelgeuse was just the beginning. Once astronomers knew what to look for, cool surface temperatures combined with extreme luminosity, they started finding more giants: Antares, Aldebaran, Arcturus. And then deeper in the sky, farther from Earth, they found the supergiants. Stars like VY Canis Majoris, discovered in the 1800s, but not understood until the 1970s when infrared astronomy revealed just how massive it truly was. Stars like RW Cephei, KY Cygni, and Mu Cephei, red titans, glowing faintly in constellations most people had never even heard of. Here's the strange part, though. These stars weren't hidden because they were faint. They were hidden because they were obscured. Many of the largest stars ever discovered sit deep within clouds of gas and dust, the remnants of stellar winds and past eruptions. When a supergiant star sheds its outer layers, which they do constantly as they age, that material forms a kind of cocoon around them. And while the star itself is blazing with light, much of that light gets absorbed by the surrounding dust and re-emitted as infrared radiation. To the naked eye, the star disappears. To an optical telescope, it looks dim and unremarkable. But to an infrared telescope, an instrument that can see heat instead of visible light, the star reveals itself, bright, bloated, beautiful in its enormity. This is why so many supergiant stars weren't discovered until the late 20th century. We didn't have the technology. The infrared astronomical satellite launched in 1983 revolutionized our understanding of cool, massive stars. Suddenly, we could peer through the dust. We could see the red supergiants in all their glory, and what we found was humbling. Some of these stars were so large that light would take hours to travel from one side to the other. Hours, not seconds, not minutes, hours. If you stood on the surface of one of these stars, assuming you could survive, which you absolutely could not, It would take you longer to walk around it than it has taken for all of recorded human history to unfold. Let me give you a specific example. VY Canis Majoris. Located about 300 to 800 light-years away in the constellation Canis Major, this star is one of the largest ever measured. Research shows that its radius is roughly 1,420 times that of the Sun. If you placed it at the center of our solar system, its surface would extend beyond the orbit of Saturn. Saturn, that's nearly 900 million miles from the Sun. And this is just one star, not a solar system, not a nebula, a single solitary star. VY Canis Majoris is so luminous that it radiates about 300,000 times more energy than the Sun. And yet, when it was first cataloged in the 1800s, no one knew. It looked like a faint reddish smudge. It took over a century of observation, infrared imaging, and spectroscopic analysis before we understood what we were looking at. And here's where the story gets even more layered. As technology improved, as our instruments became more precise, we kept finding larger stars. Bigger than VY Canis Majoris. Bigger than anything we thought possible. Stars like NML Cygni UY Scuti Westerlund 126. Each discovery pushed the boundaries a little further. Each time we thought we'd found the limit, the universe showed us something larger. And every time the process was the same, not stumbling across it by accident, not seeing it with the naked eye, but carefully, methodically analyzing light, measuring spectra, calculating distances, trusting the math even when the numbers felt absurd. This is the part most people don't appreciate. The largest stars weren't discovered by someone looking through a telescope and shouting, "Wow, that's huge." They were discovered by scientists staring at graphs, at spectral lines, at photometric data, and recognizing patterns that didn't fit the models. They were discovered by people willing to ask, what if that faint, cool star is actually massive? What if it's just far away, or obscured, or radiating most of its energy in wavelengths we can't see? Discovery is patience. Discovery is doubt. Discovery is trusting that the universe is stranger than it looks. And the lesson here, the quiet truth beneath all of this, is that we almost missed them. We almost never found the giants. If spectroscopy had never been invented, if infrared astronomy had never been developed, if a few curious scientists hadn't decided to look at old stars in new ways, we would still think the universe was small. We would still think stars were modest, comprehensible, limited. We would be wrong, but we wouldn't know it. And that's the terrifying part, isn't it? How much are we still missing? What other titans are out there hiding in wavelengths we haven't learned to detect, burning in corners of space we haven't thought to examine? The universe doesn't hand us answers. It makes us work for them. It hides the giants behind dust and distance, behind the limits of our own perception. And then, if we're clever enough, if we're patient enough, it lets us find them. Not because it wants to be understood, but because the clues were always there. We just had to learn how to read them. There's something deeply human about that. About looking at something familiar, a star, a point of light, and realizing it's something else entirely. Something older, larger, more powerful. And the beautiful part is that the discovery never stops. Every decade we find larger stars. Every year our instruments get more sensitive. Every measurement refines the last. The universe keeps whispering its secrets, and we keep listening. Slowly, carefully, one spectrum at a time. The invisible titans were never invisible. They were just waiting. Waiting for us to build the right tools. Waiting for us to ask the right questions. Waiting for us to stop trusting our eyes and start trusting the light. And now that we've found them, now that we know they're out there, the question shifts. It's no longer, are there giant stars? It's, how giant can they get? And more importantly, what are they? Because size is just the beginning. The real story is what these stars are made of, how they burn, how they live, and how they die. That's where the wonder deepens. That's where the universe stops being just large and starts being strange. There's a certain kind of beauty in something ancient and tired, a tree bent by centuries of wind, a mountain worn smooth by rain, a face lined with years of smiling. And in the cosmos, there are stars like this too. Stars that have lived long enough to grow soft around the edges, to swell with age, to glow red and slow and impossibly vast. We call them red supergiants, and they are in many ways the most beautiful monsters the universe has ever made. These are not the young hot stars burning blue and violent. These are not the bright sparks that grab your attention. Red supergiants are the old souls of the galaxy. Stars that have already lived millions of years, burned through most of their fuel, and are now drifting toward the end. But their ending is not quiet. Their ending is magnificent. Because as they die, they don't shrink. They expand. They inflate like a slow breath held too long, growing larger and cooler and more luminous until they become something almost unrecognizable. A star that was once the size of our sun becomes a titan. A giant becomes a supergiant, and the cosmos watches patient as the transformation unfolds. Let me tell you about one of them, Betelgeuse. You've probably heard the name. It's one of the most famous stars in the night sky, marking the shoulder of Orion the Hunter. On a clear winter night, you can see it easily, a bright reddish spark just above Orion's belt. It pulses softly, variably, like a heartbeat slowing down. And that's fitting, because Betelgeuse is dying. Not tomorrow, not next year, but soon by cosmic standards. Sometime in the next 100,000 years, maybe sooner, Betelgeuse will explode in a supernova, so bright it will be visible during the day. For a few weeks, we'll have two suns in the sky, and then it will fade, and Betelgeuse will be gone. But right now in this moment, Betelgeuse is still here, still breathing, still glowing. And it's enormous. Scientists suggest that Betelgeuse has a radius roughly 700 times that of our sun. If you placed it at the center of our solar system, its outer layers would swallow Mercury, Venus, Earth, and Mars. We would be inside it, orbiting within its atmosphere. And the strangest part, it wouldn't feel like fire, not the way we imagine fire. Betelgeuse's surface temperature is only about 3,500 Kelvin, cool by stellar standards. If you could somehow stand on its surface without being crushed by gravity or incinerated by radiation, it would feel more like a warm oven than a furnace. The light would be dim, reddish, almost cozy. And yet the sheer scale of it, the fact that this warm, gentle glow extends for hundreds of millions of miles, is what makes it terrifying. It's not violent, it's just vast. Red supergiants like Betelgeuse reach this size because of what happens deep inside them. When a massive star is young, it burns hydrogen in its core, fusing it into helium. This process is efficient, stable, and can last for millions of years, but eventually the hydrogen runs out. The core contracts, the temperature rises, and the star starts burning helium, fusing it into carbon and oxygen. This process releases less energy than hydrogen fusion, but it's enough to keep the star alive for a while. Then the helium runs out too, and the star, desperate to keep burning, starts fusing heavier elements: carbon, neon, oxygen, silicon. Each stage produces less energy than the last. Each stage burns faster, and as the core contracts and heats up, the outer layers of the star do something unexpected. They expand. This happens because of radiation pressure. Deep in the core, the star is burning so intensely that it's producing an enormous amount of energy. That energy pushes outward against the force of gravity, trying to collapse the star inward. And in a red supergiant, the balance tips toward expansion. The outer layers puff up, growing larger and cooler, while the core continues to shrink and heat. It's like a balloon being inflated from the inside. The surface moves farther and farther from the center, spreading the light over a larger area, which is why red supergiants glow cool and red instead of hot and blue. They're not burning less. They're just spreading the fire over a canvas too large to stay bright. Research shows that this expansion can be dramatic. A star that was 10 times the radius of the sun can swell to 500 times, 1,000 times, even 1/500 times its original size, in just a few 100,000 years. That sounds like a long time, but in the lifespan of a star, it's the blink of an eye. It's like watching someone age a lifetime in fast forward. Young, stable, mature, bloated, gone. And here's where it gets deeply poignant. Red supergiants don't explode because they're burning too fast. They explode because they're burning too slow. The core is producing less and less energy, and eventually it can't fight gravity anymore. When the core finally runs out of fuel, when it's nothing but iron, which can't be fused into anything heavier without consuming energy instead of releasing it, the core collapses. Instantly. In less than a second, a core the size of Earth compresses into a sphere maybe 20 miles wide. The outer layers no longer supported fall inward at nearly a quarter of the speed of light, and when they hit the incompressible core, they bounce. That rebound sends a shockwave outward, tearing the star apart in a supernova. The red supergiant doesn't fade, it detonates. And for a brief moment, it outshines entire galaxies. But we're not there yet. Right now, stars like Betelgeuse are still in the swelling phase, still expanding, still glowing. And they're doing something else too, something beautiful and essential. They're shedding mass. Red supergiants have powerful stellar winds, streams of particles that flow outward from their surfaces, carrying away bits of the star into space. Some believe these winds are driven by radiation pressure, the light from the star pushing on atoms and molecules hard enough to lift them away. Others suggest it's pulsations in the star's outer layers, rhythmic expansions and contractions that fling material outward. Either way, the result is the same. Red supergiants are constantly losing mass, creating vast clouds of gas and dust around themselves. Over time, these clouds can extend for light years, becoming nebulae nurseries for new stars. Take a star like VY Canis Majoris. It's one of the largest red supergiants ever discovered, with a radius estimated at around 120 times that of the Sun. If you placed it where our Sun is, its surface would extend past the orbit of Saturn. But what makes VY Canis Majoris even more remarkable is the material around it. Observations show that it's surrounded by a massive nebula of ejected gas and dust material the star has been shedding for thousands of years. This nebula contains silicates water vapor, carbon compounds, some of the building blocks of planets and life. VY Canis Majoris is not just dying, it's creating. It's feeding the cosmos. And when it finally explodes, that material will be scattered across light years, seeding future star systems with the elements needed to form rocky planets, atmospheres, oceans, maybe even life. This is the paradox of red supergiants. They're monsters, yes. They're enormous, unstable, violent in their own slow way. But they're also gentle. They give more than they take. They burn themselves out, creating the materials that make everything else possible. And there's something almost heartbreaking about that. The largest stars in the universe, the ones with the most mass and the most power, are also the most generous. They don't hoard their light. They don't cling to their atoms. They spend everything they have, and then they give even more. Let's talk about another one. Antares. It sits in the heart of the constellation. Scorpius, glowing red and steady, often called the rival of Mars because of its color. Antares is a red supergiant about 450 light years away, with a radius roughly 680 times that of the Sun. It's cooler than Betelgeuse, around 3,400 Kelvin at the surface, but it's just as luminous, about 10,000 times brighter than our Sun. And like Betelgeuse, Antares is variable. Its brightness changes over time, pulsing gently as the star expands and contracts. Scientists suggest this pulsation is caused by instabilities in the outer layers, waves of pressure moving through the star's atmosphere like ripples on water. Each pulse takes months, sometimes years. It's a slow rhythm, a tired heartbeat, the star breathing in and out as it drifts toward its end. But here's what fascinates me about Antares. It has a companion star, a smaller, hotter star, orbiting nearby, glowing blue-white in stark contrast to Antares' deep red. The companion is much younger, much smaller, probably only about 7 times the mass of the Sun. But because it's so hot, it's almost as bright as Antares in visible light. The two stars orbit each other every fun 200 years or so, locked in a slow cosmic dance. And one day when Antares explodes, that companion will be caught in the blast. It might survive, it might not. Either way, it will be forever changed, bathed in the radiation and debris of its partner's death. There's something deeply moving about that, about two stars sharing a life only for one to end catastrophically while the other watches. This brings us to a common mistake people make when they think about red supergiants. They assume these stars are rare. They assume something so large, so extreme, must be an anomaly. But red supergiants are not uncommon. They're just short-lived. Any star born with more than about 8 times the mass of the Sun will eventually become a red supergiant. It's a stage in the life cycle of massive stars. The reason we don't see more of them is that this phase is brief. A star might spend millions of years on the main sequence burning hydrogen steadily, but it might only spend a few 100,000 years as a red supergiant before it explodes. So, at any given moment, there are relatively few red supergiants visible in the galaxy. But over time, over billions of years, there have been countless millions of them, each one swelling, glowing, shedding, and dying, each one contributing to the chemical evolution of the cosmos. And that's the lesson here, the quiet truth beneath all the numbers and the sizes. Red supergiants are not aberrations. They're inevitabilities. They're what happens when a massive star grows old. They're the universe's way of recycling, of taking hydrogen, the simplest element, and through pressure and time and fire, transforming it into carbon, oxygen, nitrogen, iron, all the elements that make planets, atmospheres, oceans, and bodies. Every atom of oxygen in your lungs was made in the core of a red supergiant. Every atom of carbon in your bones. Every atom of iron in your blood. Red supergiants are not just stars. They're foundries. They're the reason we exist. There's a phrase in astronomy, "We are made of star stuff." Carl Sagan said it, and it's been repeated so many times it almost feels cliché. But it's true. And more specifically, we are made of red supergiant stuff. Because while smaller stars can create some heavier elements, only the most massive stars that become red supergiants can create the full range of elements needed for life. Only they burn hot enough live violently enough to fuse atoms all the way up to iron. And when they explode, they scatter those atoms across the galaxy, where they eventually coalesce into new stars, new planets, new chances for complexity to emerge. So, when you look at Betelgeuse, when you see that red spark in Orion's shoulder, you're not just looking at a dying star, you're looking at a factory, a forge, a place where the universe is quietly, patiently making the ingredients for everything that comes next. And the star doesn't know this. It doesn't have intention or purpose. It's just burning, just expanding, just following the laws of physics as they apply to something with that much mass and that much heat. But the result is creation. The result is us. Red supergiants swell not out of greed but exhaustion. They expand because they can't hold themselves together anymore, because gravity and pressure have been fighting for millions of years, and pressure is finally winning. And in that expansion, in that slow, inevitable bloating, the star becomes something new, something larger, something softer. It stops being a point of light and becomes a world unto itself, a sphere of glowing gas so vast that light takes hours to cross it. And it glows red because red is the color of endings. Red is the color of coolness, of energy, spreading thin, of fire that's no longer fierce but merely warm. There's a kind of peace in that, a kind of grace. The largest stars in the universe are not raging, they're resting. They're drifting towards silence, growing larger and quieter as they go. And when the end comes, when the core finally collapses and the star tears itself apart, it's not a failure, it's a release. It's the star giving everything it has, left scattering itself across the cosmos so that something else can begin. Even stars grow tired. Even light learns to rest. And in their exhaustion, they become gentle monsters, beautiful in their size, terrifying in their softness, red and slow and utterly incomprehensibly vast. But red supergiants are not the only giants. There are others. Stars that burn hotter, faster, brighter. Stars that don't swell gently, but blaze with a fury that makes red supergiants look calm by comparison. And those stars, those blue hypergiants, live by entirely different rules. If red supergiants are the tired elders of the cosmos, blue hypergiants are the young warriors, reckless, brilliant, burning with such intensity that they seem to defy the very laws that govern stars. They don't grow old gracefully. They don't swell and soften. They rage. They flare. They live fast and die violently. And in their brief, furious existence, they reshape the space around them. These are the stars that make astronomers nervous. The stars that shouldn't exist, but do. The stars that push physics to its breaking point and then push a little further. Blue hypergiants are rare, extraordinarily rare. In the entire Milky Way galaxy, with its 200 to 400 billion stars, we've identified only a handful of confirmed blue hypergiants. Why? Because they burn so hot so fast that they don't last. A red supergiant might live for a few 100,000 years in its swollen phase. A blue hypergiant might only exist in that state for a few tens of thousands of years, maybe less. They're born massive, often 100 to 300 times the mass of our sun. And they burn through their fuel with such ferocity that their lifespans are measured in cosmic blinks. They're here blazing and then they're gone. Supernovae, hypernovae, black holes. Whatever they become, it happens fast. Let me introduce you to one of the most famous, R136A1. Located in the Tarantula Nebula, a massive star-forming region in the Large Magellanic Cloud, about 160,000 light-years away. R136A1 holds the record for being one of the most massive stars ever discovered. When it was first identified and measured in detail around 2010, scientists were stunned. Research shows that R136A1 has a mass roughly 215 times that of the Sun. That's not a typo. 215 solar masses. At birth, it may have been even larger, perhaps 265 solar masses, but it's been shedding mass through powerful stellar winds ever since. And despite losing all that material, it's still the heavyweight champion of known stars. But here's what makes R136A1 truly extraordinary. It's not just massive, it's hot. Incredibly hot. Its surface temperature is estimated at around 53,000 Kelvin. To put that in perspective, our sun's surface is about 5,800 Kelvin. Betelgeuse, that giant red star we talked about earlier, is around 3,500 Kelvin. R136A1 is nearly 10 times hotter than the sun. And because it's so hot, it glows blue-white, almost ultraviolet. Most of the light it produces is in wavelengths we can't even see with our eyes. If you could somehow look at R136A1 from close up without being instantly vaporized, it wouldn't look like a warm yellow sun or a cool red giant. It would look like a searing electric blue point of pure energy. Blinding. Alien. Beautiful in a way that feels almost hostile. And the luminosity. Oh, the luminosity. R136A1 is so bright that it radiates about 6.2 million times more energy than the sun. Let that settle for a moment. 6 million times. If you placed R136A1 where our sun is, Earth wouldn't just be uninhabitable. It would be vaporized, stripped of its atmosphere in seconds. The oceans would boil away. The crust would melt. The planet itself would be torn apart by radiation pressure. Even if you moved Earth out to the orbit of Neptune about 30 times farther from the sun than we are now, it still wouldn't be safe. The light from R136A1 would be intense enough to sterilize anything in the inner solar system and beyond. How does a star get this way? How does something become so massive, so hot, so violently luminous? Scientists suggest it starts with the environment. Blue hypergiants are born in regions of intense star formation, places where gas and dust are so dense that gravity can pull together enormous amounts of material in a relatively short time. The Tarantula Nebula, where R136A1 resides, is one of the most active stellar nurseries in the local universe. Thousands of stars are being born there, many of them massive. And in the chaos of all that formation, some stars end up with far more mass than they should. They're accidents in a way. Cosmic outliers, stars that collected so much material during their formation that they entered a regime of physics most stars never experience. Once a star like R136A1 ignites once nuclear fusion begins in its core, the pressure is immense. The gravitational force trying to collapse the star inward is matched by the radiation pressure pushing outward. But in a blue hypergiant, that radiation pressure is so strong that it almost wins. The star is constantly on the verge of tearing itself apart, and in fact, it does tear itself apart slowly. Blue hypergiants have the most powerful stellar winds of any known stars. Material is streaming off their surfaces at speeds of up to 3,000 kilometers per second. That's 1% of the speed of light. These winds are so strong that they carry away entire solar masses of material over the course of just a few thousand years. R136A1 is literally bleeding into space. It's losing mass constantly, relentlessly, and there's nothing it can do to stop it. This is the price of power, the cost of burning so bright. Blue hypergiants don't get to grow old. They don't get to swell into red supergiants and drift peacefully toward the end. They spend everything they have in the first few million years of their existence, and then they collapse. Some believe that stars like R136A1 will eventually shed enough mass that they'll transition into a cooler phase, becoming yellow or even red hypergiants before they explode. Others suggest they'll skip that phase entirely and go straight to supernova. Either way, the ending is catastrophic. When a star with 200 solar masses explodes, it doesn't just become a supernova. It becomes a hypernova, an explosion so powerful it can briefly outshine the entire galaxy it's in. And what's left behind is not a neutron star. It's a black hole, a massive hungry void in space where a star used to be. Let's talk about another one, the Pistol Star. Hidden deep within the Pistol Nebula, near the center of our galaxy, about 25,000 light-years away, the Pistol Star is one of the most luminous stars known. It's not quite as massive as R136A1 estimates place it at around 100 to 150 solar masses, but it's just as extreme in other ways. The Pistol Star is so bright that it radiates roughly 1.6 million times the energy of the Sun. And it's surrounded by a massive nebula of its own, making a cloud of gas and dust that the star ejected in a series of violent eruptions thousands of years ago. That nebula is so large that it contains enough material to make several solar systems. It's the star's past scattered around it, like echoes of old violence. What's fascinating about the Pistol Star is that it's likely in transition. Right now it's classified as a blue hypergiant, but it's cooler than R136A1 with a surface temperature around 11,800 Kelvin. Some researchers believe the Pistol Star may have once been even hotter and more massive, but it's been shedding material so rapidly that it's cooling down. It might be heading toward a yellow or red hypergiant phase, or it might explode before it gets there. No one knows for sure. Blue hypergiants are so rare and so short-lived that we don't have enough examples to fully understand their evolutionary paths. They're mysteries, outliers, stars that exist at the edge of what's physically possible. And here's where the danger comes in. Blue hypergiants are unstable, not in the way that all stars are unstable, constantly balancing gravity against pressure, but genuinely profoundly unstable. They flicker, they flare, they erupt. One of the most famous examples of this instability is a star called Eta Carinae. Now, Eta Carinae is not currently classified as a blue hypergiant. It's more accurately described as a luminous blue variable, but its history is instructive. In the 1840s, specifically between 1837 and 1856, Eta Carinae underwent what's now known as the Great Eruption. For nearly 2 decades, the star brightened dramatically, becoming one of the brightest stars in the southern sky. It wasn't a supernova, it was something stranger. The star expelled an enormous amount of mass, possibly 10 to 20 solar masses, in a series of violent outbursts. That material formed the Homunculus Nebula, a beautiful hourglass-shaped cloud that still surrounds the star to this day. No one is entirely sure what caused the Great Eruption. Some theories suggest it was a massive instability in the star's outer layers, triggered by radiation's pressure overwhelming gravity. Others propose it was a collision or near miss with a companion star. Either way, Eta Carinae survived, barely. And it's still there, still glowing, still unstable. Astronomers monitor it constantly, wondering if it will erupt again, wondering if the next eruption will be the last. Because when Eta Carinae finally does explode, and it will be one of the most spectacular supernovae in recorded history. It's only about 7,500 light-years away, close enough that the explosion will be visible during the day. Close enough that it might even have measurable effects on Earth's atmosphere, though likely not dangerous ones. This brings us to a common misconception. People often assume that the largest stars are the most stable, that something so massive, so powerful must be enduring. But the opposite is true. The largest, most massive stars are the most fragile. They live on a knife's edge, constantly fighting against their own energy. A star like our Sun is stable because its mass is modest. The inward pull of gravity and the outward push of radiation pressure are nearly balanced, and they stay balanced for billions of years. But a star like R136A1, or the Pistol Star, is too massive for that balance to hold. The forces are so extreme that even tiny fluctuations can trigger massive changes. A slight increase in core temperature can cause a spike in energy production, which pushes the outer layers outward, which causes a drop in temperature, which reduces energy production, which allows the layers to fall back inward. The star oscillates, pulses, flickers like a flame in the wind, and sometimes those fluctuations grow large enough that the star loses control entirely. It erupts. It sheds mass. It transforms. And here's the beautiful, tragic irony. The stars that burn the brightest are the ones that live the shortest. The stars with the most power are the ones most doomed. It's almost Shakespearean. A blue hypergiant is born with unimaginable potential, enough mass to create heavy elements, enough energy to ionize entire nebulae, enough gravity to eventually collapse into a black hole that might persist for trillions of years. But it never gets to reach that potential gradually. It has to spend everything immediately. It has to burn at maximum intensity from the moment it ignites until the moment it dies. There's no middle ground, no coasting, no rest, just fire. Constant, relentless, unsustainable fire. Research shows that blue hypergiants lose mass at such extraordinary rates that they might shed 50 to 100 solar masses over their entire lifetimes. Imagine that. A star born with 200 solar masses might die with only 100. It's given away half of itself to the cosmos, blown into space on winds faster than anything we can comprehend. And that material doesn't just vanish. It spreads out, cools down, mixes with the interstellar medium, and eventually becomes part of new stars, new planets, new chances for complexity. Blue hypergiants, for all their violence, are contributors. They're generous. They take the raw hydrogen of the early universe and transform it into carbon, nitrogen, oxygen, magnesium, silicon, all the elements needed for life. And then they fling those elements outward at relativistic speeds. They don't hoard. They can't. They're too hot to hold anything in. There's a phrase in astronomy, live fast, die young, leave a beautiful corpse. It's usually applied to massive stars in general, but it fits blue hypergiants perfectly. They live for only a few million years, sometimes less. They die in explosions that can be seen across the universe. And what they leave behind, whether it's a neutron star, a black hole, or a scattered nebula of enriched gas, is a legacy, a mark on the cosmos. Proof that they existed, even if only briefly. But here's the question that haunts me. Do blue hypergiants know they're doomed? Obviously not. They're not conscious. They don't think. They don't feel. But there's something almost poignant about a star that's too powerful for its own good. A star that can't help but destroy itself. It's burning at 53,000 Kelvin because that's what the physics demands. It's shedding mass because radiation pressure gives it no choice. It's heading towards supernova because once you have that much mass, that much energy, there's no other ending available. It's fate written in the equations. And the star simply follows the script. Some stars burn like rage, brief, brilliant, gone. They don't linger, they don't fade quietly into the background. They explode onto the stage, demand attention, and then vanish, leaving only light and debris and the faint echo of something that burned too bright to last. And maybe that's enough. Maybe existence doesn't need to be long to be meaningful. Maybe a star that lives for 3 million years, but transforms the chemistry of an entire region of space, has done more than a star that lives for 10 billion years in quiet, modest stability. There's a kind of beauty in something too bright to last, a kind of honesty. Blue hypergiants don't pretend. They don't hide what they are. They're power made visible, fury made luminous. And when you look at them through a telescope, through spectroscopy, through the data, you're not seeing a star at rest. You're seeing a star at war with gravity, at war with its own energy, at war with time itself. And it's losing. It will always lose. But in the losing and the struggle, it creates something extraordinary. Light that crosses galaxies, elements that seed planets, black holes that warp space, a legacy that outlasts the star by billions of years. But for all their power, for all their intensity, blue hypergiants raise another question. A question about measurement, about certainty. Because how do you know a star is 215 solar masses? How do you measure something that's 160,000 light years away, hidden in a nebula, shedding mass constantly and flickering with instability? How do you trust the numbers when the object itself is barely understood? Imagine trying to weigh a mountain while standing at the base of it. You can't lift it. You can't put it on a scale. You can't even walk around it completely. All you have is the shape of its shadow, the angle of the sun, and the laws of physics. That's essentially what astronomers face when they try to measure a star, especially a star that's thousands of light years away, shrouded in dust, pulsating unpredictably and bleeding mass into space. How do you measure something you can never visit? How do you weigh something you can never touch? And more importantly, how do you know your answer is right? The truth is, we don't always know. Stellar measurements are educated guesses, sophisticated estimates built on layers of assumptions. And those assumptions can change. When a new technique is developed, when a better telescope comes online, when someone recalculates the distance or revises the temperature model, the numbers shift. Stars that were once the largest suddenly get smaller. Stars we'd never heard of suddenly become giants. The universe doesn't change. Our ability to see it does. And that gap between reality and measurement is where all the mystery lives. Let's start with the most basic problem: distance. If you don't know how far away a star is, you can't determine its true size. A star that looks bright could be small and nearby, or enormous and distant. Without distance, brightness is meaningless. So the first step in measuring any star is figuring out how far away it is. And for a long time, that was nearly impossible. The stars are so far away that they don't shift position when Earth moves. They're fixed, or so it seemed. No parallax. No way to triangulate, just points of light with no depth. The breakthrough came in the 1830s. 3 astronomers, Friedrich Bessel, Thomas Henderson, and Friedrich von Struve, independently measured the first stellar parallaxes. They observed stars 6 months apart when Earth was on opposite sides of its orbit around the Sun and looked for the tiniest shift in position. And they found it. A wobble so small, it's measured in arc seconds, fractions of a degree so tiny that it's like trying to spot a coin on the moon, but it was there. Bessel measured the parallax of 61 Cygni and calculated its distance at about 10.4 light-years. Henderson measured Alpha Centauri at 4.3 light-years. Suddenly, the universe had depth. The stars weren't painted on a dome. They were scattered through three-dimensional space, some close, some unimaginably far. But parallax only works for relatively nearby stars. Beyond a few thousand light-years, the angles become too small to measure accurately, even with modern telescopes. So, for distant stars, especially the supergiants and hypergiants we've been talking about, astronomers have to use other methods. And this is where things get complicated, because every method involves assumptions. Every technique has uncertainties, and those uncertainties compound. One common method is called spectroscopic parallax, though it's not actually parallax at all. It's a clever trick based on the spectrum of a star's light. Remember, a star's spectrum tells us its temperature and chemical composition. But it also tells us something else, the density of the star's atmosphere. Hot, dense stars have sharp, narrow spectral lines. Cooler, more diffuse stars have broader, fuzzier lines. By analyzing those line widths, scientists suggest we can estimate whether a star is a dwarf, a giant, or a supergiant. A dwarf star is small and dense. A giant is large and diffuse. A supergiant is enormous and even more diffuse. Once you know what type of star it is, you can estimate its absolute brightness, how bright it would appear at a standard distance. Compare that to how bright it actually looks, and you can calculate how far away it must be. But here's the problem. That calculation depends on correctly identifying the star's type. And some stars are ambiguous. Some stars sit right on the boundary between giant and supergiant. Some stars are pulsating, changing size over time, which changes their spectral lines. Some stars are surrounded by dust that absorbs certain wavelengths, making the spectrum harder to read. Every ambiguity introduces error. Every assumption adds uncertainty. And when you're trying to measure a star that's 20,000 light-years away, even small errors become significant. A 10% error in distance translates to a 20% error in radius. A 20% error in temperature can change the estimated luminosity by a factor of 2. The numbers are slippery. They shift depending on which model you use, which data you trust, which assumptions you make. Let me give you a real example. VY Canis Majoris. For decades, this star was considered one of the largest known, with radius estimates ranging anywhere from 1/300 to 1/900 times that of the Sun. Different studies using different methods produced wildly different results. Some researchers used infrared observations and found a larger size. Others used radio wavelengths and found a smaller size. Some measured the star's brightness and temperature and calculated radius from luminosity. Others tried to directly measure the star's angular diameter using interferometry, combining light from multiple telescopes to create a virtual telescope large enough to resolve the star's disk. But VY Canis Majoris is surrounded by a thick cloud of dust and gas material it's been shedding for thousands of years. That material scatters light blurs. The edges makes it hard to tell where the star ends and the nebula begins. In 2012, a team of astronomers using the Very Large Telescope in Chile performed one of the most detailed studies of VY Canis Majoris to date. They used a technique called adaptive optics, which corrects for distortions caused by Earth's atmosphere. And they mapped the star in multiple wavelengths. Their conclusion, VY Canis Majoris has a radius of about 1/420 solar radii, give or take 120. That's still enormous and one of the largest stars known, but it's smaller than some earlier estimates. And even that number comes with caveats. The star is irregular in shape. It's not a perfect sphere. It has bright spots and dark spots regions that are hotter or cooler, denser or more diffuse. When you measure its radius, you're averaging, you're simplifying, you're turning something complex and three-dimensional into a single number. And that number is provisional. It might change if someone develops a better model. It might shift if we discover the star is closer or farther than we thought. This happens all the time in astronomy. A star is measured. The number is published. It becomes the accepted value. And then years or decades later, someone recalculates it with better data, and the number changes. Sometimes the change is small, sometimes it's dramatic. In 2013, a red supergiant called UY Scuti was measured and found to have a radius of around 700 solar radii, making it one of the largest stars known at the time. It was heralded in articles and videos as the biggest star in the universe. But then in subsequent studies, the radius was revised downward to about 755 solar radii, still enormous, but not as large as originally thought. What happened? The distance to the star was recalculated. A more accurate measurement of its luminosity was obtained. The models were refined, and the star got smaller. Not because it actually changed, but because our understanding of it improved. This is the lesson astronomers have learned sometimes painfully. Measurement is not the same as truth. Measurement is an approximation of truth, filtered through instruments and mathematics and assumptions. And the more extreme the object you're measuring, the farther away it is. The hotter it burns, the faster it pulsates, the harder it is to approximate accurately. Blue hypergiants are especially difficult because they're so unstable. They flicker, they erupt, they shed mass unpredictably. The star you measure today might not be the same star you measure a decade from now because it's literally changed. It's lost mass, it's cooled slightly, it's pulsed outward or contracted inward. You're trying to measure something that's moving, something that's evolving, something that doesn't hold still long enough for the data to settle. Another challenge is dust. Interstellar dust absorbs and scatters light, especially blue light, making distant stars appear redder and dimmer than they actually are. This effect is called reddening, and it can throw off all your calculations. If you measure a star's color and assume it's a cool red supergiant, but it's actually a hotter star that's just been reddened by dust, you'll get the wrong temperature, which gives you the wrong luminosity, which gives you the wrong size. Astronomers have to correct for reddening, but that requires knowing how much dust is between us and the star. And sometimes we don't know. Sometimes we can only guess. Every guess introduces uncertainty. Then there's the problem of binaries. Many massive stars exist in binary, or multiple star systems, orbiting around a common center of gravity. If you're measuring the light from such a system, you might be seeing the combined light of two or more stars. If you don't realize there's more than one star, you might think a single star is brighter and larger than it actually is. Conversely, if one star eclipses the other, you might think the star is dimmer. Binary systems can be detected by watching for periodic changes in brightness or by analyzing the star's spectrum for Doppler shifts indicating orbital motion. But not all binaries are obvious. Some companions are too faint to see. Some orbits are too slow to measure in a human lifetime. And if you miss the companion, your measurements are off. Research shows that some of the most massive stars, the ones that become blue hypergiants, are often found in clusters where hundreds or thousands of stars were born together. The Tarantula Nebula, where R136A1 resides, is a perfect example. The entire region is blazing with young massive stars, many of them overlapping in our line of sight. When you try to measure one star, you're also capturing light from its neighbors. You have to carefully subtract the background, isolate the target, and hope you've accounted for everything. It's painstaking work. It requires patience, precision, and a willingness to accept that the answer might be wrong. And here's the philosophical part, the part that keeps me thinking. Even when we get a measurement we're confident in, even when multiple studies agree, even when the math checks out, we're still measuring an echo. The light from VY Canis Majoris left that star 800 years ago. The photons traveling through space for millennia before they hit a telescope mirror and got turned into data. By the time we see the star, it's already changed. Maybe only slightly, maybe significantly. We're not measuring what the star is, we're measuring what it was. And if the star is variable, if it's pulsating or erupting, then the light we see today is telling us about a state that no longer exists. The star has moved on. We're studying history. This is true for all astronomy, but it's especially poignant for massive stars because their timescales are so short. A star like Betelgeuse might explode in the next 100,000 years. Maybe it already has. Maybe it exploded 500 years ago, and the light from that explosion is currently traveling through space toward us. We won't know until it arrives. We're watching the past, waiting for the future. And in the meantime, we measure, we calculate, we refine, we argue over whether a star is 1/200 solar radii or 1/500, whether it's 20,000 light years away or 25,000, whether it has 100 solar masses or 150. Do those numbers matter? In one sense, yes. Precision matters. Understanding matters. The better we can measure stars, the better we can understand stellar evolution. Nucleosynthesis supernova, the formation of black holes. The numbers inform the models predict behavior. The predictions can be tested. That's how science works. But in another sense, the numbers are just placeholders, symbols for something we can't fully grasp. Because even if we knew with absolute certainty that a star was exactly 1/420.73 solar radii, what would that tell us? What does it mean to be that large? How do you internalize a number that's incomprehensible? You can write it down, you can calculate with it, but you can't feel it, you can't hold it. You can't stand inside it and understand its edges. Uncertainty isn't failure, it's honesty. It's the acknowledgement that we're small creatures on a small planet, trying to measure things that are unimaginably distant and impossibly large. We're doing our best with the tools we have. We're building better instrument space telescopes that can see in infrared and ultraviolet interferometers that combine light from telescopes thousands of miles apart. Spectrographs that can detect chemical signatures in the faintest light. Every generation of astronomers refines the measurements, corrects the errors, gets a little closer to the truth. But the truth itself remains out of reach, asymptotic, always approached, never quite arrived at. And maybe that's okay. Maybe the pursuit matters more than the precision. Maybe what's beautiful is not the number itself, but the effort to find it, the patience, the ingenuity, the willingness to stare at a point of light and ask, what are you? How far are you? How large? And then to build an instrument, design an experiment, analyze the data, and come up with an answer, an imperfect answer, a provisional answer, an answer that might change in 10 years when someone figures out a better method, but an answer nonetheless, a step closer to understanding. The universe doesn't reveal itself all at once. It whispers and updates. Each measurement is a sentence. Each refinement is a paragraph. And over decades, over centuries, those sentences accumulate into something like comprehension. We don't know everything. We never will. But we know more than we did. We know stars can be 1,500 times larger than the sun. We know they can have masses 200 times greater. We know they burn at 50,000 Kelvin and radiate millions of times more energy. We know these things because someone measured them, someone calculated them, someone trusted the math, even when the numbers seemed absurd. And now we can look up at the night sky and see it differently. Not as a scattering of random lights, but as a population of objects, each with its own size, temperature, distance, and story. Some of them giants, some of them hypergiants, some of them so large that they barely fit within the equations that describe them. So the next question is not, how big can stars get, but which one is the biggest? And that's where the competition begins. That's where astronomers turn their instruments towards specific candidates, compare the data, and debate the results. Because somewhere out there, hidden in the vast expanse of the galaxy, there might be a star larger than any we've measured. A star so immense that it redefines what we think is possible. Somewhere in the constellation, Scutum, about 19,000 light-years from Earth, there's a star so large that if you placed it where our sun sits, its surface would stretch past the orbit of Saturn. Not just to Saturn, past it. Beyond the rings, beyond the moons, into the cold, dark expanse where sunlight is barely a whisper. This star has a name that sounds more like a catalog entry than a cosmic titan Stephenson 2/18. And as of now, based on the measurements we have, it is likely the largest star ever discovered, the current champion, the heavyweight, the one that makes even other supergiants look modest. But here's the catch: we can't be entirely sure. And that uncertainty is part of what makes it so fascinating. Stephenson 2/18 sits within a massive open cluster called Stephenson 2, discovered in 1990 by American astronomer Charles Bruce Stephenson. The cluster itself is remarkable, a dense gathering of red supergiants, one of the richest collections of such stars known in the Milky Way. There are at least 26 red supergiants crammed into this relatively small region of space, all of them enormous, all of them old, all of them nearing the end of their lives. It's like a retirement home for giants, a place where the universe's most massive stars go to swell and cool and wait for the inevitable collapse. And among them, Stephenson 2/18 stands out. Not because it's brighter than the others, it's actually quite dim from our perspective, hidden behind thick clouds of interstellar dust. But because when astronomers measured its size, they found something almost unbelievable. Research shows that Stephenson 2018 has a radius approximately 2,150 times that of the Sun. Let me put that in context. If the Sun were the size of a basketball, Stephenson 2/18 would be the size of a large stadium. If you were standing on Earth and the Sun were replaced by Stephenson 2/18, you wouldn't see a sun anymore. You'd see a wall of dim red light filling half the sky. The star's surface would be closer to you than the moon currently is. You'd be orbiting inside its outer atmosphere. And the light, oh the light. It would take about 8.7 hours for a photon to travel from one side of the star to the other. Not 8.7 minutes like it takes light to cross the distance from the sun to Earth. 8.7 hours, longer than a workday, longer than most people sleep. You could start a road trip at sunrise on one edge of this star drive all day, and the light from where you started would still be catching up to you by the time you stopped. This is the scale we're dealing with. Numbers so large they lose meaning. Distances so vast they become abstract. And yet, Stephenson 2/18 is real. It's out there right now, glowing faintly in the infrared, shedding mass into space, drifting towards supernova. We can't see it with our eyes. Even through most optical telescopes, it's invisible, obscured by dust. But infrared telescopes can pierce that veil. They can detect the heat. And what they've found is a star so immense that it challenges our understanding of stellar evolution. Here's the strange part. Stephenson 2/18 isn't the most massive star. It's not even close. Its mass is estimated at around 16 to 25 times that of the Sun, which sounds enormous to us, but is actually relatively modest for a red supergiant. Stars like R136A1, which we talked about earlier, have over 200 solar masses. So, why is Stephenson 2/18 so much larger? The answer lies in how it's burning. Stephenson 2/18 is old. It's already burned through most of its hydrogen and helium. It's now fusing heavier elements in its core, carbon, oxygen, maybe even silicon, and that process is far less efficient than hydrogen fusion. The core is contracting, heating up, desperately trying to stay alive. And as the core contracts, the outer layers expand, they puff up, they spread out. The star becomes a balloon, inflated by radiation pressure from the core, but held together only loosely by gravity. Its density drops, its surface cools, and its radius grows enormous. Scientists suggest that stars like Stephenson 2 Toliad 18 are near the theoretical limit of how large a star can get. If it grew much larger, the outer layers would be so loosely bound that they'd simply drift away into space. The star would evaporate. There's a balance, a delicate equilibrium between the radiation pushing outward and the gravity pulling inward. And Stephenson 218 is riding that edge. It's as large as a star can be without ceasing to be a star. Any bigger, and it would just become a nebula with a hot core in the middle. But measuring Stephenson 218 has not been easy. The star was cataloged decades ago, but its true size wasn't understood until relatively recently. In the early 2000s, astronomers using infrared surveys started analyzing the Stephenson 2 cluster in detail. They measured the star's luminosities, temperatures, and spectra. They calculated distances using a combination of methods: parallax measurements for nearby reference stars, main sequence fitting for the cluster as a whole, and spectroscopic techniques to estimate individual stellar properties. And when they crunched the numbers for Stephenson 2 Toliad 18, they realized they were looking at something extraordinary. A star with a luminosity of around 440,000 times that of the Sun, and a surface temperature of only about 3,200 Kelvin. Those two numbers combined pointed to an object of staggering size. But those numbers come with error bars, margins of uncertainty. The distance to the cluster is uncertain by a few thousand light years. The temperature measurement depends on modeling the star's spectrum, which is complicated by dust, and by the fact that the star's surface is irregular and mottled. The luminosity calculation requires assumptions about how much light is being absorbed by interstellar dust. Every step of the process involves estimates, corrections, approximations. And when you feed uncertain inputs into an equation, you get uncertain outputs. The radius of Stephenson 218 could be 150 solar radii. It could be 2,000. It could be 2,300. We don't know for sure. And that means the title of largest star is provisional. It's the best answer we have right now. But it might change. In fact, it has changed. For years, a star called UY Scuti held the title. Discovered in 1860 by German astronomers at the Bonn Observatory, UY Scuti was initially just another variable star, one of thousands cataloged and then largely forgotten. But in 2012, a team of astronomers re-examined it using modern instruments and found that it was far larger than anyone had realized. Initial estimates placed its radius at around 1,700 solar radii, making it the largest known star at the time. Articles were written, videos were made. UY Scuti became famous. And then a few years later, the measurements were revised. The distance to the star was recalculated, the temperature was refined, and the radius shrank to about 755 solar radii. Still enormous, still a supergiant, but not the largest. Stephenson 218 took the crown, and it's held onto it for now. But somewhere in the galaxy there might be an even larger star waiting to be discovered. Or the measurements might change again. The crown might pass to another. That's the nature of this kind of science. It's competitive, it's iterative, it's humble in the face of vastness. Let me give you a thought experiment to help you grasp the scale. Imagine you're standing on Earth and someone asks you to walk around Stephenson 2 Toliad 18. Just walk along the surface at a comfortable pace, 3 miles per hour, stopping only to sleep. How long would it take? The circumference of Stephenson 2 Toliad 18 is about 9 billion miles. At 3 miles per hour walking 8 hours a day, it would take you approximately 3 million years to complete the loop. 3 million years. That's longer than modern humans have existed, longer than most mammal species survive. You'd walk past ice ages, past the rise and fall of civilizations that haven't even been imagined yet, and you still wouldn't be done. That's how large this star is. It's not just big, it's incomprehensibly, absurdly, almost offensively large. And yet, from Earth, Stephenson 2 Toliad 18 is invisible. It doesn't dominate the sky, It doesn't inspire myths or navigation or poetry. It's hidden, forgotten, a whisper in the data. And that tells you something profound about the universe. The largest things are not always the most visible. The most powerful objects are not always the ones we notice. There are titans out there burning quietly, swelling slowly, waiting for their final moments. And we only know about them because someone pointed a telescope in the right direction, captured the right wavelengths, did the math, and realized what they were seeing. There's something deeply humbling about that. About the fact that a star 2,000 times larger than the sun can exist, and we almost missed it. About the fact that it took us until the 21st century to even find it. About the fact that there are probably others we still haven't seen. The universe is not arranged for our convenience. It doesn't highlight the important things. It doesn't label the extremes. It just is. And we, with our tiny telescopes and our fragile instruments and our provisional measurements, are trying to map it, trying to understand it, trying to find the edges of what's possible. But here's the question that haunts astronomers who study stars like Stephenson 2, Sirius 18. How much longer does it have? Red supergiants in this phase of life are unstable. They're losing mass. They're pulsating. They're drifting toward core collapse. Some believe Stephenson 218 could explode in the next few thousand years. Others suggest it might last for tens of thousands of years or even longer. We don't have precise models for stars this large because they're so rare. We don't have enough examples to test our theories. We're guessing based on physics, on simulations, on extrapolations from smaller stars. And the truth is, we won't know until it happens. Until one night, a bright new light appears in the constellation Scutum. A light that wasn't there before. A light visible during the day, bright enough to cast shadows lasting for weeks or months before it fades. That will be Stephenson 218 dying, exploding, becoming a supernova. And when it does, it will scatter its atoms across light years of space. Carbon, oxygen, silicon, iron, all the elements forged in its core released. All the material that will someday become new stars, new planets, maybe even new life. But we won't see it when it happens. Not really. We'll see it 19,000 years after it happens. Because that's how long it takes light to travel from Stephenson 218 to Earth. The explosion could have already occurred 10,000 years ago, 5,000 years ago, last Tuesday, and we wouldn't know. The light is still on its way, still crossing the void, still carrying the message of the star's death. And when it arrives, when that light finally reaches Earth and astronomers detect the sudden brightening, they'll point their instruments at it. They'll study the spectrum. They'll measure the energy. They'll watch as the light fades over weeks and months. And they'll write papers about it. They'll update the models. They'll learn something new about how the largest stars die. But the star itself will already be gone, long gone, a memory traveling through space. Do you ever think about that? About the fact that when you look at the stars, you're looking at the past, not metaphorically, literally. The light from Stephenson 218 left that star 19,000 years ago. When that light began its journey, humans were still painting on cave walls. We hadn't invented writing. We hadn't built cities. We were small tribes scattered across the continents, looking up at the same sky, seeing the same stars, not knowing what they were. And now, 19,000 years later, that light arrives. And we catch it with a telescope, and we analyze it, and we calculate that the star it came from is 150 times larger than the sun. That's the gift of light. It carries information across unimaginable distances. It lets us study things we can never visit. It connects us to the past, to the far reaches of the cosmos, to events that happened long before we existed. And in that sense, Stephenson 218 is not just a star. It's a time capsule, a message from 19,000 years ago, telling us what the universe was doing while we were still learning to be human. And the beautiful part is that the message is still being written. The star is still shining, still shedding light, still sending photons our way. And every night some of those photons hit a telescope somewhere on Earth. And we learn a little more. We refine the measurements, we update the models. We get closer to understanding what it means to be that large, what it costs, what it creates. Still, there's a lingering uncertainty. Is Stephenson 218 really the largest? Or is there something bigger? Something we haven't found yet lurking in a dusty corner of the galaxy? Some astronomers believe there could be even larger stars in regions we haven't surveyed thoroughly. Stars hidden in dense molecular clouds, stars too cool and dim to stand out in visible light stars that require infrared or radio observations to detect. The galaxy is vast. We have only mapped a fraction of it in detail, and every time we look deeper, we find something new, something unexpected, something that makes us revise our understanding. So, for now, Stephenson 218 holds the title, the largest star we know of, the current champion. But that title comes with an asterisk, with a caveat, with the acknowledgement that we might be wrong, that the measurements might change, that another star might take its place, and that's okay. That's the nature of discovery. It's not about finding the final answer. It's about finding the next answer, the better answer. The answer that gets us a little closer to understanding how large a star can be, how the universe works, what's possible within the laws of physics. And in the end, the size is just a number, a measurement, a way of quantifying something that's fundamentally unquantifiable. Because what does it mean to be 150 times larger than the sun? How do you hold that in your mind? How do you grasp it? You can write it down, you can calculate with it, but you can't feel it. You can't stand inside it and understand its edges. It's too large for comprehension, too strange, too far beyond the scale of human experience. And maybe that's the point. Maybe the largest stars exist to remind us that the universe is bigger than we can imagine, that there are things out there that dwarf us, not just physically, but conceptually, that no matter how much we learn, no matter how precise our measurements become, there will always be something just beyond our reach, something waiting to surprise us, something that makes us look up and whisper, how is that even possible? But size is not the end of the story, because eventually even the largest stars run out of time. Eventually the core collapses. The outer layers fall inward, and the star that once stretched past Saturn becomes something else entirely, something smaller, denser, darker. And that transformation that death is where the real drama begins. Every giant carries its ending inside itself. From the moment it ignites from the first fusion of hydrogen into helium, the clock starts ticking. Not loudly, not urgently, but inevitably. And for the largest stars, the ones we've been following through this quiet journey, the ending is not gentle. It's not a slow fade into darkness. It's a violence so complete, so catastrophic, that it reshapes everything around it. The death of a giant is not an ending. It's a transformation, a rebirth, a cosmic event so energetic that it can outshine billions of stars and send ripples through space and time itself. But here's what most people don't realize. The way a star dies depends entirely on how it lived. A small star like our sun will swell into a red giant, gently shed its outer layers, and leave behind a cooling ember called a white dwarf. It's peaceful, quiet, almost dignified. But the giants we've been talking about, stars with 10, 50, 100, 200 times the mass of the sun, they don't get that option. Their deaths are written in the core in the fusion processes that sustain them in the relentless pull of gravity that can no longer be resisted. And when the moment comes, when the fuel finally runs out, the collapse happens in less than a second. One moment, a star. The next moment, an explosion bright enough to be seen across the universe. Let's start with what happens in the core. We've talked about how massive stars burn through their fuel faster than smaller stars. They start with hydrogen, fuse it into helium. Then they burn helium, creating carbon and oxygen. Then they burn carbon, creating neon and magnesium. Then oxygen, creating silicon and sulfur. And finally, silicon, creating iron. Each stage produces less energy than the last. Each stage burns faster. Hydrogen fusion can last for millions of years. Helium fusion lasts for hundreds of thousands of years. Carbon fusion lasts for a few thousand years. Oxygen fusion lasts for about a year. And silicon fusion, it lasts for a few days, maybe a week. That's it. In the final moments of a massive star's life, it's burning silicon into iron so quickly that the core is adding layers of new elements by the day by the hour, like an onion building shells around itself. Hydrogen on the outside, helium beneath, carbon, oxygen, silicon, and at the very center, iron. And iron is where it stops, because iron is different. Iron is the most stable element in the universe. Fusing lighter elements into iron releases energy, but fusing iron into anything heavier requires energy. It consumes energy instead of producing it. So, when the core of a massive star becomes iron, fusion stops. There's no more fuel, no more fire. The core is still incredibly hot, billions of degrees, but it's no longer generating the outward pressure needed to hold the star up. And gravity, which has been waiting patiently for millions of years, finally wins. The collapse is almost instantaneous. In less than a second, a core the size of Earth, containing more mass than the Sun, compresses down to a sphere about 20 miles wide. 20 miles. From thousands of miles across to the size of a small city. The atoms are crushed so tightly that electrons are forced into protons, creating neutrons. The matter becomes so dense that a teaspoon of it would weigh as much as a mountain. And the collapse releases so much gravitational energy that it heats the core to trillions of degrees. Trillions. Numbers that stop making sense. Numbers that belong to the early universe, to the Big Bang itself. And then the core rebounds. It can't compress any further because neutrons packed that tightly resist. They push back. And the rebound sends a shockwave outward, racing through the star at nearly a quarter of the speed of light. That shockwave hits the outer layers, the shells of silicon, oxygen, carbon, helium, hydrogen, and blasts them into space. The star explodes. We call it a supernova. And for a few weeks, that single exploding star can shine as brightly as an entire galaxy. It can outshine 100 billion stars. It can be visible across millions, even billions of light years. It's one of the most energetic events in the universe, rivaled only by the collision of black holes or neutron stars. But supernovae are not all the same. The way a star explodes, the brightness of the explosion, the elements it creates all depend on the mass of the star that died. A star with 10 to 25 solar masses will produce what's called a Type II supernova. These are the most common supernova from massive stars. They're bright, but not extraordinarily so. They leave behind a neutron star, a dense spinning remnant that might become a pulsar, sending out beams of radiation like a cosmic lighthouse. But stars more massive than 25 solar masses, stars like the blue hypergiants and the largest red supergiants, they don't just become supernovae. They become hypernovae. Explosions so powerful that they're in a category of their own. And what they leave behind is not a neutron star, it's a black hole. Let me take you back to a specific moment in history. February 23, 1987. Astronomers in the southern hemisphere noticed a new point of light in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way about 160,000 light-years away. At first they thought it might be a nova, a relatively small stellar explosion. But as they watched, the light kept growing, brighter, brighter. Within days it was visible to the naked eye. Within weeks it was one of the brightest objects in the southern sky. They named it Supernova 1987A, and it became the closest supernova to Earth, observed in nearly 400 years. The last time humans had seen a supernova this close was in 1604, before telescopes were even common. This was a once-in-a-lifetime event, and astronomers around the world turned every instrument they had toward it. What they saw changed our understanding of stellar death. Supernova 1987A came from a blue supergiant called Sanduleak, 69 degree 2, not a red supergiant like most models predicted. a blue one. And that was surprising. Scientists had to rethink their models. They realized that massive stars don't always follow a simple path. Some stars swell into red supergiants and explode. Others lose their outer layers through stellar winds, shrink back down, become blue supergiants again, and then explode. The evolution is messier than we thought, more variable, less predictable. And SN 1987A gave us a front-row seat to that process. Observations showed that the explosion released an unimaginable amount of energy, about 10^44 joules, roughly the amount of energy the sun will produce over its entire 10 billion year lifetime, released in a matter of seconds. Most of that energy didn't even come out as light. It came out as neutrinos, ghostly particles that barely interact with matter. Detectors on Earth, massive tanks of water buried underground, picked up a burst of neutrinos from SN 1987A. Just a handful, maybe 20 or 30 particles. But that was enough, because neutrinos travel at nearly the speed of light and pass through almost everything. Detecting them confirmed that the core had collapsed, that a neutron star had formed, and for the first time, we had direct evidence of what happens inside a supernova. We weren't just seeing the explosion, we were feeling it, measuring it, confirming the theory with data. And SN 1987A is still there, still glowing. The light has faded, but the remnant remains the expanding shell of gas and dust, glowing in the energy of the explosion, slowly spreading into space. Someday that material will cool. It will mix with the interstellar medium. It will become part of new stars, new planets, maybe even new life, because that's what supernovae do. They don't just destroy, they create. Every atom in your body heavier than hydrogen was made inside a star, and most of those atoms were scattered into space by a supernova. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it came from exploding stars. You are made of supernova debris. You are stardust assembled into something that can think and wonder and look back at the stars that made you. But the largest stars, the ones with 100 or 200 solar masses, they don't just create supernovae, they create hypernovae. Explosions 10 to 100 times more energetic than a standard supernova. And sometimes they create something even stranger, a pair instability supernova. This happens when a star is so massive that the photons in its core, the particles of light, start turning into matter, specifically into electron-positron pairs. And when that happens, it removes energy from the core, which causes the core to contract, which increases the fusion rate, which releases more energy, which creates more photons, which create more pairs. It's a runaway process, a feedback loop. And it ends with the entire star core and all being ripped apart in an explosion so violent that nothing is left behind. No neutron star, no black hole, just debris. A cloud of gas expanding at thousands of kilometers per second, glowing with the heat of its own destruction. Scientists believe this is what happened to some of the first stars in the universe, the population 3, stars born from pure hydrogen and helium before there were any heavy elements. Those stars could have been 200, 300, even 500 solar masses. And when they died, they exploded, completely seeding the early universe with the first carbon, oxygen, silicon, iron. Without those explosions, there would be no planets, no rocky worlds, no chemistry complex enough to support life. The death of the first giants made everything else possible. Research shows that most massive stars, though, leave behind black holes. When the core of a star more massive than about 25 suns collapses, the neutrons can't hold it up. The gravity is too strong. The core keeps collapsing past the neutron star stage, past any known state of matter, into a singularity, a point of infinite density where the laws of physics break down. And around that singularity, space itself warps so severely that nothing, not even light, can escape. That's a black hole, a region of space-time so twisted that it becomes a one-way door. Anything that crosses the event horizon, the boundary of no return, is gone, pulled inward, crushed, destroyed at the quantum level. and we can never know what happens inside. We can only see the effects on the outside, the way nearby stars orbit something invisible, the way gas spirals inward, heating up, glowing in X-rays as it falls, the way space-time itself bends around the absence. And here's the paradox. The largest stars, the ones with the most mass, the most power, the most presence, become the smallest objects. Or the darkest. A star that was 2,000 times the size of the sun collapses into a black hole that might only be a few dozen miles across. The event horizon is small. The mass is compressed into something incomprehensibly dense. It's as if the universe takes everything the star was, all its light, all its heat, all its size, and crushes it down into silence, into a void, into a place where even time behaves strangely, where clocks slow down, where the future and past twist into each other. The biggest stars leave the smallest corpses, or the darkest ones. But that darkness is not empty. It's heavy. It's dense. It's full of everything the star used to be, compressed into a space so small that it defies imagination. And over billions of years, those black holes might merge with others. They might grow. They might become the supermassive black holes at the centers of galaxies, the ones with millions or billions of solar masses, the ones that shape the orbits of entire star systems. The death of a single giant becomes part of the architecture of the cosmos. It becomes a gravitational anchor, a sculptor of space, a reminder that endings in the universe are never final. They're just transitions. There's a certain poetry in that. The largest things collapse into the smallest. The brightest objects become the darkest. And yet in their collapse, they don't vanish. They transform. They change form. They persist in a new way, as gravity is curvature, as an absence that paradoxically has presence. You can't see a black hole, but you can see what it does. You can see stars orbiting nothing. You can see gas glowing as it spirals inward. You can see the way light bends around it, creating gravitational lenses, warping the view of galaxies behind it. The black hole is there, invisible but undeniable, silent but powerful, a scar in space-time where a giant used to be. And the explosion, the supernova or hypernova that created it, sends elements out into the galaxy. Carbon, oxygen, silicon, iron, magnesium, sulfur, all the building blocks of planets and life. Those atoms drift through space for millions of years. They cool, they condense, they become part of molecular clouds, the nurseries where new stars form. And eventually they coalesce into planets, into oceans, into atmospheres, into cells, into bodies, into you. Every breath you take contains oxygen made in the core of a dying star. Every thought you think is powered by chemical reactions involving carbon, nitrogen, phosphorus elements, forged in stellar furnaces and scattered by supernovae. You are not separate from the giants. You are their echo, their legacy. You are what happens when a star dies and its atoms get a second chance. A chance to become something complex, something conscious, something that can look up at the night sky and wonder where it came from. Endings aren't empty. They're heavy with everything that was. They're full of possibility. They're the moment when transformation happens, when one form of existence gives way to another. A star becomes a black hole. A supernova becomes a nebula. A cloud of gas becomes a planet. A planet becomes life, and life becomes thought, becomes memory, becomes the ability to tell stories about stars and supernovae and black holes. The universe is not a straight line, it's a cycle. Death feeds birth, destruction enables creation, and the largest stars in their most violent moments are the most generous. They give everything. They scatter their atoms across light years. They enrich the galaxy. They make the next generation possible. They don't disappear. They collapse into silence so deep even light can't climb out. But that silence is not absence. It's presence compressed. It's weight. It's memory. It's the imprint of a star that once burned brighter than galaxies, now folded into space-time waiting. And someday in the far, far future, when the universe has cooled and the last stars have died, those black holes will be all that's left. The final monuments to the age of light. The last echoes of the giants that once filled the cosmos with fire. But we're not there yet. Right now in this moment, the giants are still here, still burning, still shedding light, still carrying their endings inside themselves, patient, inevitable. And that brings us full circle, back to the beginning. Back to the question that started this journey. What does it all mean? What are we supposed to feel when we realize we're made of stars? When we understand that the light in the sky is old, that the atoms in our hands are ancient, that we are part of something so much larger and stranger than we ever imagined? There's a phrase that keeps coming back to me as we reach the end of this quiet journey. A phrase so simple it almost sounds like poetry, but it's not poetry. It's physics, it's chemistry, it's the literal, observable, measurable truth. Every atom in your body was once inside a star. Not metaphorically, not symbolically, actually, physically. The carbon in your cells, the oxygen in your blood, the calcium in your bones, the iron that carries oxygen through your veins, all of it was forged in the heat of a massive star in temperatures hotter than anything we can create on Earth, and then scattered into space when that star exploded. You are not separate from the cosmos. You are made of it. You were made of giant light. Let me take you back to the beginning. Not the beginning of this story, but the beginning of everything. About 13.8 billion years ago, the universe came into existence in an event we call the Big Bang. In those first moments, in the first 3 minutes, the universe was so hot and dense that nuclear fusion happened everywhere. Protons smashed together, creating helium and trace amounts of lithium. But that's it. Just hydrogen, helium, and a tiny bit of lithium. No carbon, no oxygen, no iron, no silicon. None of the elements that make up planets, oceans, or bodies. The early universe was chemically simple, beautiful in its simplicity, but lifeless. Because life as we know it requires complexity. It requires heavy elements. And the only place heavy elements can be made is inside stars. The first stars formed about 100 to 200 million years after the Big Bang. Massive stars made purely of hydrogen and helium, burning in a universe that had never seen carbon or oxygen. Scientists call them population 3 stars, and none of them exist anymore. They all died. They lived fast, burned bright, and exploded in supernovae or hypernovae, scattering the first heavy elements into the void. Those atoms drifted through space mixed with hydrogen and helium, and eventually collapsed into the next generation of stars. And those stars, slightly enriched with carbon and oxygen, lived and died and scattered even more elements, generation after generation, cycle after cycle. Each generation of stars enriching the galaxy, creating more complex chemistry, building up the periodic table one explosion at a time. Our sun is a late arrival. A third-generation star, maybe fourth born about 4.6 billion years ago, from a cloud of gas and dust that was already rich in heavy elements. That cloud contained the debris of countless dead stars, supernovae that exploded millions or billions of years earlier, their atoms drifting, cooling, waiting. And when our solar system formed, when the planets coalesced from the leftover material around the sun, those atoms became part of Earth. They became the crust, the mantle, the oceans, the atmosphere. And eventually they became life, became cells, became organisms, became you. Research shows that the process of nucleosynthesis, the creation of elements, happens in layers inside massive stars. Hydrogen fuses into helium in the core. When the hydrogen runs out, the core contracts and heats up, and helium fuses into carbon and oxygen in a shell around the core. When the helium runs out, carbon fuses into neon and magnesium. Then oxygen fuses into silicon and sulfur. Then silicon fuses into iron. Each layer is burning a different element, like an onion made of fire. And when the core collapses and the star explodes, all those layers are blasted into space. The carbon from the helium-burning shell, the oxygen from the carbon-burning shell, the silicon, the sulfur, the iron, all of it scattered, all of it mixing with the interstellar medium, all of it eventually finding its way into new stars, new planets, new chances for complexity. But here's the part that gets me, the part that makes me pause and just feel the weight of it. The iron in your blood, the iron that binds to oxygen and carries it through your body, the iron that lets you breathe, that lets you think, that keeps you alive, was made in the final moments of a dying star. In the silicon-burning shell, just days before the core collapsed. That iron atom has been on a journey. It was forged in temperatures of billions of degrees. It was blasted into space in a supernova explosion, traveling at thousands of kilometers per second. It drifted through the galaxy for millions of years. It became part of a molecular cloud. It condensed into a grain of dust. It accreted onto a growing planet. It became part of Earth's mantle, then the crust, then the soil. It was taken up by a plant. It was eaten by an animal. It passed through the food chain. And eventually it became part of you. That single atom has traveled across space and time, through explosions and oceans and ecosystems, just to end up in your body and your blood, doing the quiet essential work of keeping you alive. Every atom has a story like that. Every element in your body is a traveler. The calcium in your bones came from a supernova. The oxygen you're breathing right now came from a red supergiant that exploded before Earth even existed. The carbon in your DNA, the molecule that encodes everything about you, was made in the helium-burning shell of a star that died billions of years ago. You are not made of Earth. Not really. You are made of stars. You are a collection of ancient atoms recycled and reassembled, given temporary form, walking around on a planet made of the same stuff. The universe made you, literally, physically, from its own substance. And the beautiful part, this process is still happening. Right now, somewhere in the galaxy, a massive star is in its final days. It's burning silicon into iron. Its core is on the verge of collapse. And in a few days or a few weeks or a few years, it will explode. It will scatter its atoms across light years. And those atoms will drift. They'll cool. They'll mix with gas clouds. And eventually, millions or billions of years from now, they'll become part of a new star system, maybe a new planet, maybe new life. The cycle continues. The universe recycles itself. Death becomes birth. Endings become beginnings. And the largest stars, the red supergiants and blue hypergiants we've been talking about, are the engines of that cycle. They're the forges. They're the reason complexity exists. They're the reason you exist. There's a study published in the Astrophysical Journal in 2017 that traced the origins of the elements in the human body back to specific stellar processes. The researchers broke it down element by element. Hydrogen from the Big Bang, carbon and oxygen from low-mass stars in their red giant phase and from supernovae, nitrogen mostly from intermediate-mass stars, iron from supernovae, and heavier elements like gold and platinum from neutron star collisions. Every element in your body has a different origin story, a different cosmic pathway. You are not just made of stars, you are made of many stars, of different kinds of stars that lived and died in different ways at different times in different parts of the galaxy. You are a mosaic, a synthesis, a living, breathing collaboration between billions of years of stellar evolution and cosmic chemistry. Do you feel it? That connection, that continuity. You are not a separate thing looking at the universe from the outside. You are the universe looking at itself. You are a way for the cosmos to know itself, to experience itself, to wonder about itself. Carl Sagan said it best, "We are a way for the cosmos to know itself." And it's true. The atoms in your brain, the ones firing right now as you listen to this, as you think about stars and supernovae and the origins of elements, those atoms were once in stars. They were once part of something burning at millions of degrees, fusing lighter elements into heavier ones. creating the raw materials for everything that would come later. And now, those same atoms are arranged in such a way that they can think, they can remember, they can feel wonder. The universe made atoms that can contemplate the universe. That's not just beautiful, that's extraordinary. And it's humbling, isn't it? To realize that you're not the center of the story. You're part of the story, a chapter, a moment, a brief arrangement of ancient atoms that will someday disperse again, return to the earth, return to the cycle. The atoms that make up your body right now will outlast you by billions of years. They'll become soil, water, air. They'll be taken up by plants, by animals, by future organisms we can't even imagine. They'll continue. They'll persist. They'll keep traveling. And maybe someday, billions of years from now, one of your atoms will be part of a new star, a new planet, a new being looking up at the sky and wondering where they came from. There's a kind of immortality in that. Not the kind where you personally live forever, but the kind where the substance of you, the physical material that makes you continues. It endures, it transforms, it becomes part of something else, something new, something that carries forward the legacy of stars and supernovae and the long, patient work of the universe turning hydrogen into complexity. You are temporary, but you are made of things that are not. You are a pattern, a configuration, a momentary expression of something eternal. And that brings us back to the largest stars, the ones we've been following through this journey. Betelgeuse, Antares, Vive Spy Canis, Majoris, R136A1, Stevenson, Staubitze 18. Stars so large that they barely fit within our equations, so bright that they flood space with light so massive that their deaths reshape galaxies. These stars are not just interesting astronomical objects. They're essential. They're necessary. Without them, there would be no heavy elements, no planets, no oceans, no life, no you. The largest stars are the most generous. They spend everything. They burn hot live briefly and give it all away in a final catastrophic explosion. They don't hoard their atoms. They scatter them. They seed the galaxy with the raw materials for everything that comes next. And we sitting here on a small planet orbiting a modest star are the beneficiaries of that generosity. We are the children of giants. So, when you look up at the night sky, when you see Betelgeuse glowing red in Orion's shoulder, or Antares burning in the heart of Scorpius, remember, you're not just looking at distant lights. You're looking at family, at ancestors, at the forges that made you possible. Those stars are not separate from you. They're connected to you by chemistry, by physics, by the simple, undeniable fact that the atoms in your body came from stars like them. Stars that lived, burned, and died so that you could exist. And one day when those stars explode, when Betelgeuse finally goes supernova, when Antares collapses into a black hole, they'll scatter even more atoms into space. And those atoms will drift and cool. And eventually, millions of years from now, they'll become part of something new. Maybe a new star, maybe a new planet, maybe new life looking up at the sky, wondering where they came from, not knowing they were made of Betelgeuse, made of Antares, made of ancient light. The stars didn't die, they scattered, and some of them became you. You are not a separate thing, you are stardust. You are recycled atoms. You are the universe experiencing itself, looking back at the stars that made you feeling a connection that goes deeper than thought, deeper than words, down to the molecular level, down to the atomic level, down to the fundamental truth that we are all made of the same substance. We are all children of the cosmos. We are all, in the most literal sense, made of giant light. And I think there's something comforting in that. Something peaceful, because it means you're not alone. You're not isolated. You're part of something vast and ancient and ongoing. You're part of a cycle that's been running for billions of years and will continue for billions more. You're part of the universe's way of creating complexity, of building structures, of making things that can think and feel and wonder. You're not an accident. You're a result. A consequence of physics playing out over cosmological timescales, a pattern that emerged because stars burned and died and scattered their atoms. And that pattern, that configuration of ancient stardust is you, right now, in this moment, listening, thinking, wondering. Sleep well, dream gently, and remember, you were made of light that traveled far to be here. Light that once burned in the cores of giants. Light that crossed the galaxy, drifted through nebulae, condensed into planets, became life, became thought, became the ability to look back at the stars and understand finally where you came from. You are not small, you are vast, you are ancient, you are the universe waking up to itself, and that is the most beautiful thing I know. Thank you for staying with me through this journey. Thank you for listening. Thank you for letting these stories of giants and supernovae and ancient light settle softly into the quiet spaces of your mind. If you found peace in this, if you felt something shift, if the stars seem a little closer now, a little more familiar, then this time we spent together has meant something. And I'll be here again with another story, another journey through the cosmos, another chance to drift quietly into wonder. Until then, rest well. Look up when you can, and know that the stars are not distant. They're inside you. They always have been. Good night.